Okay, so we have seen that RSA is insecure without padding. Yeah, textbook RSA is insecure. So we're just gonna pad our messages. So in order to avoid this, okay, I'm just taking the cube root kind of attack. We're gonna make our number bigger that we want to encrypt. So we take our AES key that we want to encrypt to send it to our recipient, and we're just gonna append 0 bytes to the end, right? So now we have a message that is something like AES key and then 000. If I take this padded message as an integer and print it, I can see that, okay, this is my AES key here, and this is the padding. This right here is the padding. Now this number is really big, so the modules will take effect because I will take this big number here to the power of my public exponent. Now, is that a good idea? Well, no, because if you think about it, what appending 0 bytes here actually does is, if you look at it from the perspective of numbers, you have this AES key and you multiply it with the power of 2, right? Power of 2 in hexadecimal or in binary is always 1 and then many zeros. So it's actually our original AES key multiplied with the power of 2. Well, since we know this factor, this power of 2, we can just multiply the ciphertext with the inverse of our padding in order to receive the original AES key by taking the root. Okay, so what do I mean by that? Well, we have AES key times padding to the power of e. This is the ciphertext. Well, if now I take the inverse of the padding and also encrypt it with the public key, raise it to the power of e, if I multiply those two ciphertexts together, p and its inverse will obviously cancel out, since the definition of the multiplicative inverse was that this is 1, right? The element multiplied with its inverse. So then the paddings have cancelled out. We have just the small message, which is our AES key. And then we can again just take the root. This is called the Darping Pad.